Hi, I'm Akshat Sharma. I'm a TME tech lead at Cisco, and I primarily handle XR and a lot of the operational and the automation requirements around it. So what we'll cover today is an RFC compliant implementation of secure zero touch that's coming out with iOS XR. And I think it's quite exciting to actually have this gear up with a lot of the stuff that's going out for both the 5G and the data center deployments from the XR portfolio. So we'll kind of see how that matches up, and we can go into more details therein. All right, so before I start off, let me give you a quick background on what we've done with Classic ZTP. There's a reason why it's called Classic ZTP now, because secure ZTP is on its way, and this Classic ZTP workflow is something that you'll see in a similar fashion across vendors. Essentially, your box boots up, there's no config on it. It's going to send out DHCP messages, V4 or V6. You typically have a DHCP server, and you'll have a certain set of options that you'll use to identify your device, classify it, give it an IP, give it the specific options that it needs. For example, for V4, you'll give it option 67, a boot file name. And that ends up giving you either the location, the URL to download a CLI config directly, or a ZTP script. In the XR land, we support, well, frankly, any type of binary packaging that you need, but we, of course, support natively Python and Bash libraries, which allow you to do just about anything on the box in terms of automation. So typically, you would expect that customers have their ZTP scripts lying on a web server. Based on the option URL given to the device, the script gets downloaded or the config, and it gets executed subsequently. So the device basically gets provisioned to a certain state as needed with just these three components in play. The router, basically with no config or anything on it, the DHCP server to get it the IP and the options that it needs, and then the web server to download stuff. Now, keeping that in mind, what do we actually do with it? We can apply configs, we can deploy applications, whether they're on-box containers, binaries, cron jobs, whatever you want to set up. You have several software upgrade and downgrade workflows that you can work with. So you can actually utilize your scripts to do a bunch of upgrades and downgrades. And you can even do that subsequently in the day one, day two lifecycle of the device as well. And of course, you get access to just about all the automation libraries that you need. So you can use CLI, you can use the YAG models, etc., right on day zero. And that's the basic set of functionalities that you typically want to cover. And yeah, it depends on you in terms of the amount of complexity you want to have on day zero versus day one or and above. So if you want to pack, let's say, NSO into your workflow, you typically have a ZTP script followed by NSO, bringing in the entire shebang of what you want to run on the device. And as I mentioned, we have a well-established Python and Bash library available on the box. So you can basically get access to either the CLI or the XML format for the YAG models to work with. Typically, we've seen that most customers are still really conversant with CLI automation on day zero, and they tend to prefer that. So you definitely have exhaustive library covering that. And that gives you a quick background on Classic ZTP. What we want to consider, however, is where is it lacking? Well, first of all, where do we want to play? Now, iOS XR for the longest time has covered several parts of the service provider network. And for the first time with some of our boxes that came out, particularly the NCS 540s, we also started focusing a lot more on the access side of the service provider market. And when you consider that part of the deployment, including several requirements around the 5G access, we start considering the basic requirements for ZTP primarily because of the sheer scale of devices that you're trying to deploy. And remember, this is topology agnostic. So you don't really care about whether it's a ring topology or a hub and spoke or a hierarchical setup. Irrespective of how they're connected, you need to figure out a mechanism for either all or some of your devices to be bootstrapped in a zero-touch fashion, and make sure that they're able to connect back either to a centralized location or to multiple centralized locations, as the case may be. So keeping that in mind, there are three basic items that you can think of. One, of course, you would have a tree-based build-out strategy. So if you have sort of a tree that you're building out, you know that irrespective of the topology, if one device has access to a set of services like the DHCP and web server, it can act as a relay for the next set of devices that connect to it, and you can build out quite organically. And we've done several deployments in this fashion, and really just becomes topology agnostic once you're able to figure out the correct relay configurations that get applied in sequence across these devices as they come up. And of course, security is critical, right? So once you start considering where these devices are going, they could be in shared NOCs, they could be on top of a telephone pole. You're basically trying to make sure that you have a way to trust the device that joins the network, and if possible, allow the device to trust the network that is joining, right? And that's the level of security that you're looking for when you bring these devices in. And bear in mind, this works for several data center deployments as well. And we're talking to a lot of tier one web customers that are actually super interested in getting a secure workflow on day zero ZTP. And of course, there are several other components coming in with VLAN discovery. I'm not going into those details today, but even if you have a layer 2 cloud in the middle, figuring out how to discover the VLAN on which the DHCP request must be sent out is something that a bare bone naked device needs to do when it comes into the network. So there's several mechanisms at play there. But as I mentioned, the talk today is primarily on the security aspect, so we'll focus there. Another important point to consider is the fact that the ZTP implementations are very similar, but really different across vendors. I'm just giving you a quick snapshot without naming names of the type of options that you have in play, right? The options that you send out from the device to the DHCP server and what you get back from the DHCP server varies across vendors. Those who know which vendors I'm talking about. And as a result of this, what happens is that there is an abstraction that the operator then has to take care of to deal with this sort of disjoint complexity on the operational side, and then figure out how to make things work in a consistent fashion. It goes without saying that you need to get to a system where you can standardize these workflows and not really depend on vendor-specific options that have been designed over a period of time. So keep these in mind. We basically have a system today that allows you to automate on day zero, but it has no security in play, right? So you can basically go ahead and download complete malware, and except for a few checks, most of the devices would run it across vendors. There is no way for the device to trust the network today, nor does the network trust the device. And lastly, there is no standardization at all in terms of the DHCP options that are utilized. And that is precisely where we start thinking about enabling trust in the ZTP workflow. I think this is fairly obvious to most people. Security and convenience don't go together, right? So we need to find a sweet spot where we can get our end-to-end security as we need it, and but still get a zero-touch workflow going. We absolutely do not want to make it a one-touch workflow where people have to get a bunch of devices in a pre-staging facility and then figure out how to securely transport them to the actual install site. So what is that sweet spot? In order to achieve security for ZTP, there are three basic things that you're trying to do. One, when the router joins the network, you need to validate that it is the router that it's claiming to be. Secondly, the router itself, without any config on it, needs to validate that it accepts the network that it's trying to join. And lastly, the artifact, which could be config, scripts, and with the new ZTP workflow images, these artifacts that are downloaded are signed and therefore accepted by the router on day zero. Keep these three aspects in mind, and we'll combine these together to understand how the RFC basically plays out. Hardware root of trust. So in order to accomplish any of those three aspects that I mentioned, you need hardware root of trust. You absolutely cannot begin with trust that begins in the software, because there would be no way to uniquely claim that a device is, let's say, a Cisco device and a device belonging to a particular customer, bought by a given customer, unless you have trust that is anchored in the hardware. And that is precisely where we come to the Cisco TAM. If you know about, let's say, TPM 2.0, you know more or less most of the things around Cisco TAM. But one of the main aspects that you should remember is that all of the keys here are signed by Cisco. There are certain keys in particular, like the Cisco SUDI here, that are very relevant to the secure ZTP workflow. And we basically make sure that based on the keys that are being utilized, these can be inserted only by Cisco manufacturing or can be changed only by Cisco manufacturing, which basically ensures that you have supply chain protection from the get-go. So there is more storage available on the TAM, which allows customers to bring their own keys as well. But you have a certain set of Cisco keys already there that allow you to basically have trust on the supply chain for the device that's being shipped out to you. And therefore, the SUDI becomes extremely important. IEEE 802.1AR compliant. We basically have SUDI, a secure unique device identifier, that is essentially a certificate, right? So it contains your PID, the type of platform that you're trying to identify, and of course the public key associated with that particular device, for which the corresponding private key is also burned into the TAM. This is extremely important because we're going to utilize the SUDI to identify the device and also uniquely challenge it to prove that it is the device that we're talking about. So in order to establish this sort of unique identity, this is the structure that is utilized. Based on the UEFI secure boot spec, I believe 2.3.1 is the first one that started off with it. You have a bunch of keys, PK, KEK, the DBDBX setup that allows you to have a bunch of keys signed by Cisco in the chip, which is with TAM. And then you have a few more locations, particularly the on-chip secure storage that you see here, which can also allow you to bring in certificates from the customer into play, right? So in addition to that, there's also one more aspect, which I think would be important to understand as we go through it, which is the feature control flags. So we are also introducing a new secure flag called the secure ZTP flag, which will also be used to make sure that a device only does secure ZTP if it's enabled. Right, so keep these in mind. We're going to use the TAM, particularly the SUDI certificate within it, and the enable disable secure ZTP flag to make sure that the device does secure ZTP only when it is shipped out by Cisco manufacturing. Right, so what are we trying to accomplish? Before we do secure ZTP, you have to establish ownership on a device. So a Cisco device is shipped out to a customer site. It is a Cisco device, but it is not owned by the customer. So as part of the day zero workflow, you want to ensure that when the device does get provisioned on the install site, you can go ahead and push some sort of ownership credentials onto the device as part of the day zero workflow, ensuring that the ownership is established as part of secure ZTP. What we therefore want is that if you take your own certificate, so the customer creates their own, let's say, OpenSSL certificate, or they have some certificates already lying around, they can go ahead and use that owner certificate, burn it into the TAM using the on-chip secure storage. And if that happens, you basically have a device that can then utilize it for subsequent features and applications, etc., allowing you to have ownership establishment on the device. But that's a little hard to do. How do you get a certificate on a naked device that doesn't trust anything at this point and make sure that it is accepted into the device in a trustworthy fashion? That's where the first RFC that we care about comes in, RFC 8366. RFC 8366 basically gets you ownership vouchers. This is where it starts getting interesting because we're actually stitching together a couple of pieces that leads us to the secure ZTP workflow. This is the Yang model from RFC 8366 that describes what an ownership voucher is. What you care about are a couple of things: a serial number and a PIN domain certificate, or a PDC. What this means is that for a given device, you can create an ownership voucher that contains the serial number of that device alone, and it contains sort of the root certificate for the owner cert that we want to burn into the TAM, right? So to establish ownership, you want to burn an owner certificate into the TAM. The root certificate, or at least a certificate down in the chain of the owner certificate, is placed in an ownership voucher along with the serial number of the device. If you keep just these two items in mind, what you get to is this basic workflow. I have a bare-bone device with a TAM, and I use an ownership voucher which contains the trust chain for the owner certificate. And as long as the ownership voucher is trusted by the device, it'll accept the owner cert, burn it into the TAM. And why does the device actually care about the ownership voucher? Well, because this ownership voucher will be signed by the vendor, in this case, Cisco. And that is how you create a trust chain where the device accepts the signature of the ownership voucher based on the keys that are already burned by Cisco manufacturing into the TAM, uses that to validate the owner cert, and pushes it into the TAM. And you have ownership establishment effectively. This is essentially RFC 8366, right? But it is the auxiliary RFC. So you've considered the classic ZTP workflow earlier, a DHCP server, web server, and the device interacting with each other. And you can see the ownership establishment through RFC 8366 here. So we'll combine the two together, and you basically get RFC 8572, which is secure ZTP. How do you get the OV for the router? What we've done is we've gone ahead and created a cloud-based MASA service, basically a manufacturer authorized signing authority. That's what it stands for. And this particular entity is allowed to give you a signed ownership voucher based on cloud APIs that you can access. And you can basically use that to fetch the ownership voucher, place it on a secure ZTP server, which is RFC compliant. In this case, Cisco Crosswork SZTP server is one such example. And that way you have a way to create a trust chain for certificates that will be accepted by the device in the secure ZTP workflow. And of course, you can use the APIs directly to also be able to push the ZTP servers for on-prem rollout. So you don't necessarily need internet access just to get to the MASA service in all cases. So there are several automation options available here. And therefore, I come to essentially my last couple of slides, which is tying all of this together. RFC 8572, the standardized implementation of ZTP that will ensure that you finally have potentially a multi-vendor sort of deployment possible, a cross-vendor implementation of ZTP, and something that is secure end-to-end. How do you do it? You get a device, bare bone, shipped by Cisco manufacturing. There's a DHCP server, completely untrustworthy. So we're not going to use it to actually give us all of the information on what to install and what to run. We'll only use the DHCP server now to give us option 143 or 136 based on V4 or V6, whatever you're using, and use that to allow the device to reach out to a ZTP server as defined in RFC 8572. There will be a bunch of YANG model interactions between them. And all of this happens over an HTTPS session. And this allows your device to then download signed artifacts that can be run, right? So you've basically extended the original classic ZTP workflow, but you have a few more complex elements added. How does this in the end work out? You have router validation as one of the first steps you need to accomplish. How does the network trust the device? I spoke about the SUDI certificate, the secure unique device identifier that is burnt into the TAM, both the public and the private key. The device offers the SUDI cert to the ZTP server upon joining the network. The ZTP server will go ahead and do a challenge response, make sure only the device that contains this SUDI certificate is the one that is essentially corresponding. And then you end up having a router validation on day zero. And the second aspect, which is how does the device trust the network? This happens basically through the workflow you see here. There is bootstrapping data coming from the ZTP server to the device, and we follow the trust chain that we spoke about earlier. There is an owner certificate backed up by the ownership voucher provided by Cisco, signed by Cisco, and all of your artifacts, scripts, configs, redirect URLs are also signed by that owner certificate that you now trust. You use all of this information in a single bootstrapping data context and give it to the device. the device will validate it and accept it because it trusts the ownership voucher, therefore the owner's cert, and hence the signature on the artifact, which contains the scripts, configs, etc. And what you end up accomplishing is basically a workflow where router client validation, step number 1, and the network domain validation, step number 2, are both accomplished in a couple of workflows. The SUDI certificate is used by the network or the ZTP server to validate the device. And finally, the device validates the network based on the bootstrapping data that at a minimum contains the ownership voucher signed by Cisco, that is the vendor.
How crucial is that to have the ZTP, the service provider field? Because in the SP, you don't typically see that they are rolling out the hundreds of devices every day, right? So in the enterprises, it's really important to have that. But how can you clarify that? What operational meaning it has in the SP?
Actually, it has quite a lot of relevancy on the SP side. When you look at specifically, as I mentioned, the access deployments, and particularly the 5G access deployments, you have several hundreds of sites that are coming up at a given point in time, right? And those sites typically are handled by third-party vendors in a lot of different countries. Some of them are handled directly by the network operators themselves. But essentially what you expect there is that in a given site, you may have a bunch of devices, let's say 10 to 20 devices coming up in a ring. And then in another site, you do the same thing and again. So what you end up doing is that today you're used to maybe deploying a certain set of devices at a time, and you may structure that over a few days or few weeks or few months. But with secure ZTP in particular, what you're trying to do is accomplish a lot of these deployments over a period of a few days or a couple of weeks, so that you're able to get a lot of these sites up and running almost immediately. So we do actually see a lot of the high numbers going out with access deployments, and a couple of our customers, both in Europe and in the US, are actually looking at exactly this workflow. Deploy out, let's say, a bunch of NCS 540s going into the access side in several different sites, and these would go from 100 to thousands in numbers based on the number of sites you deploy at a time.